Exact joins split one person into multiple records as soon as a name or address changes. Splink's Fellegi Sunter model turns fuzzy field evidence into match probabilities and reliable clusters. You'll learn how the pieces fit into a workflow that blocks candidate rows and links fuzzy duplicates into explainable clusters. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Lots of teams run into the same plumbing problem. Your database contains the same person or company several times. A typo or an alternative spelling breaks exact joins. That causes wrong counts, duplicated marketing, and billing headaches. Probabilistic entity resolution treats each field as noisy evidence and combines those signals to decide whether two rows refer to the same real-world entity. Fellegi Sunter boils down to this: how likely is agreement or disagreement on each field? And how do those odds combine into an overall match probability? If the name looks similar and the birth date lines up, the combined probability goes up. If the date disagrees, it drops. The result is graded, explainable decisions instead of brittle true or false rules. We'll walk a tiny demo that mirrors a real task. You'll prepare a small people table, limit comparisons with blocking, add a fuzzy name comparison, score pairs, inspect the evidence that produced a score, and finally turn confident links into clusters. This mirrors a customer or vendor dedupe workflow you can adapt. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we create a controlled toy table and a local SQL backend, so the rest of the steps have a concrete dataset to act on. This snippet creates a tiny people table and a Splink DuckDB API backend. Exact joins break as soon as John Smith becomes John Smythe, even though the birth date still lines up. The people data frame keeps the input readable. One stable unique ID, one typo-prone name, and one useful DOM. DuckDB API gives Splink a local SQL execution backend without introducing a separate service. The visible output confirms the record count and backend, so we know the demo has a concrete dataset before matching begins. After creating this small table, you can see the two records that represent the same person with different spellings, which makes the next steps meaningful. Blocking candidate pairs massively cuts the work. We still need a fuzzy name scorer and a way to treat date agreement as separate evidence. This example configures a Splink Fellegi Sunter style dedupe model for typo-tolerant matching. Comparing every row to every other row gets expensive fast, so block-on DOB limits candidate pairs to records sharing a birth date. Levenshtein at thresholds, name 2, adds a fuzzy name comparison, while exact match DOB treats birth date agreement as separate evidence. The configured probabilities are small teaching values, but they show how Splink combines agreement and disagreement rather than using one brittle rule. The output shows one candidate block and 5 model records, which means the matcher is ready to score pairs. In practice, you would tune thresholds and prior probabilities based on a labeled sample or business tolerance for false merges. Next, we ask the model to score those blocked pairs, so we can see which pairs look most like duplicates. This code asks Splink to score the blocked candidate pairs and surfaces the strongest match. The expensive work happens in linker.inference.predict, which returns pairwise predictions rather than immediately merging records. As Pandas data frame brings the results back for inspection, and sort values makes the ranking deterministic for debugging and tests. Keeping top, left, right, and score separate mirrors a production review queue. first score, then decide what to trust. The output shows the highest probability pair, turning messy text into a ranked duplicate candidate. You can use this output to build a human review queue or to calibrate the probability threshold for automated merges. A probability is only useful if humans can see the evidence behind it. So we extract the comparison levels that produce the score. This snippet turns a high score into something an engineer can inspect during an incident. A probability alone is hard to trust, so Splink includes gamma columns that record which comparison level each pair reached. The code collects those columns, converts the selected top pair into simple integers, and prints the levels for gamma name and gamma dob. This is useful when a threshold suddenly starts merging the wrong customers or companies. The output shows the evidence levels behind the selected pair, which makes the match auditable instead of opaque. In a support situation, those gamma columns point straight to the fields you should review or to a parameter to retune. Finally, we need clusters, not just pairwise suggestions. So we turn confident links into connected groups. This example finishes the mini pipeline by converting confident pairwise matches into entity clusters. Threshold match probability equals 0.97 keeps only high confidence edges before clustering, which is a simple guardrail against over-merging. Raising that threshold usually reduces false merges, but can split real entities. Lowering it catches more duplicates, but increases review risk. Cluster pairwise predictions at threshold, then turns pair links into connected groups. And the Pandas group by counts only clusters with more than one record. The output shows how many duplicate entity groups were created and how many input records were linked. This last step is where pairwise logic becomes a concrete deduplicated table you can feed downstream. If you scale this, swap DuckDB for a distributed store and keep blocking strict. The same pipeline maps to a CRM export or a vendor registry with messy names and shared dates. Keep three things in mind. Splink applies a Fellegi Sunter style model to combine field comparisons into a match probability. Use this when you need explainable, tolerant linking across noisy tables, especially for customer or provider data. And watch out! Your threshold choices and blocking rules strongly affect recall and precision, so validate with samples. As a concrete next step, tune threshold match probability against a labeled slice of your CRM customer table, and watch how cluster counts change as you adjust it. That one parameter quickly reveals the trade-off between missed duplicates and risky merges. If practical AI engineering helps, subscribe and watch the AI engineering videos.